Okay, here's our first course in algebra, Algebra 2 that is. And we're going to talk about sets of numbers, like you're seeing, sets of numbers and notation. So let's first talk about the set. What is a set? Well, let's get a clean page, talk about a set. A set is a collection of things, whatever they are, somehow related. And every thing in that set is an element. It's an element of the set. So let's have our set. Let's just write a set, give an example. We'll say we have a set of, what should we have? Let's say superheroes. Superheroes. I think there's an E in there. And we'll call it set A. So set A, and then they have these braces. There's a brace in there. And we'll say a set of superheroes. And maybe we'll have, of course we have to have Batman, right? Yeah. Batman has to be in the set. We'll have Batman, and we'll have, who knows, we'll have Wolverine. Right? Put a little Marvel DC in there. Maybe we'll throw in Green Lantern. Haven't heard from him in a while. And maybe we'll throw in, well, Deadpool's been big lately. This summer, Deadpool. Who else? Let's throw in Thor. And maybe one more person. Who should we do? That's Hulk. Throw in the Hulk. Hulk versus Thor. So anyway, we have our set. It's a set of superheroes. Now, obviously, there's more superheroes than this, but this is it. This is our set of superheroes. And that's all there is according to this set. So it is a finite set, which I'll talk about more. Now we could have a subset of this. So you can have a subset. You're gonna see that word a lot. A subset. So a subset is every element that's in the subset is in the set, but there's more details. So it's related to the set. We could say subset B, and maybe subset B is only Marvel, right? We'll say Marvel heroes, Marvel superheroes, right? So then we can, make it more detailed on our subset. So you have sets and you have subsets. Now let's use numbers, because of course you'll see numbers a lot. So let's say we have set A. Why not begin with A? And we have our braces, and we have 0, 1, 2, 3, 4, 5, 6. What's the next number? You got it. 7, 8, and 9. So we'll leave, that's our set. And we'll define our set. We'll say, well, this set is all digits. All the known digits. Well, we wouldn't say known digits, because that's all there are. There's only 10 digits in the entire universe. All the digits. Remember, a digit is one single number. And all these digits make all the rest of the numbers. So that's our set. And so what do you think a subset could be? We'll say set B is our subset. What can we say about a subset to this? Remember, in the subset, all the elements of the set are in, well, put it this way. Whatever element you have in B in the subset has to be in set A. So we could say, what can we say? How about we say even digits? Right? Because all the even digits are in A. So what can we say? All the even digits. So if we want to define that, we'll have to start with 2. 2, 4, 6, 8. So all the even digits. Remember, 0 is not odd or even. So we have our set and we have our subset. Now we also have empty sets. Let's clear this out. Get some room here. Go back if you need it. Clear it all out. Just change the color. So you can also have an empty set. And when you see this symbol, this is the symbol for empty set. And there's nothing in it. So it contains no elements. No things. It's empty. So where would you see an empty set? So let's say we had a set of all even, let's say, prime numbers greater than 2. Do you know any? Now, if you don't know what a prime number is, let's just make sure we know. Prime numbers, right? So if you, for example, the number 2 could be broken down to 2 times 1. That's it. There's no other numbers that make 2. If you multiply to get 2, just 2 times 1. And by the way, there are no prime numbers greater than 2 that are even. So this would be an empty set. We know 4 could be broken down to 2 times 2, but it could also be broken down into 4 times 1. So there's more than 2. There's more than 2 numbers that make up 4. So 4 is not prime, 4 is composite. But you know this, right? So we have our empty sets and we have our sets. Now sets can be finite, means they're limited, like we did before, or they can be infinite, they're unlimited. Let's look at an example of that. Let's clear this out. Where's the clear button? There we go. And, no, it didn't clear. Try it again. Clear it all. And maybe we'll change the pen again. So if we have, like we had before, a set of all the digits, well, we know there's only 10 digits in the entire universe. So that would be a finite set. Finite. It's limited. That's it. But if you said the set of all integers, and we'll go over that term in a minute, well, that's infinite. So an integer, by the way, and sometimes they use the symbol z. You might not see that, but that just means Zahlen. It's a German word for number. Go figure. But integers, they're not decimals or fractions, right? So it's any number that is not a decimal or a fraction. Just the number. Like 5. Like 5 or -5. They're integers. There's no point to it. And I mean no point, no decimal point. But actually 5.0 is actually an integer because it's just 5, right? But 5.2 is a decimal, so it's not an integer. But on a number line, you can go from -infinity to infinity, and you have all those integers in between. It's an infinite set. All right, so the next thing we should talk about is the types of numbers we have. Let's clear this out again. Clear it all. Maybe we'll keep that color. And we'll start off with real numbers. And sometimes you'll see this symbol for real numbers. So they're either real numbers or they're imaginary numbers. And imaginary numbers will come up in this class. In Algebra 2, imaginary. And by the way, imaginary numbers are not fake numbers. They're actually real numbers in a way. Well, let's not confuse you yet. You'll see those symbols. You probably have seen them maybe. Perhaps that little I symbol for imaginary. They have real applications, and we'll talk about them in Algebra 2. Imaginary. So in the real numbers are all the numbers you ever learned. All the numbers you have used so far. All the numbers you have used since you were counting, since when you started counting, whether it was kindergarten or in the crib, who knows. So they're decimals. Decimals are real numbers. They're integers, which we talked about before. Integers. They're fractions. They're all these real numbers. So if I say like the square root of 25, well, that's a real number because the square root of 25 is plus minus 5, right? Because 5 times 5 equals 25. Or negative 5 times negative 5 is 25. So it's plus minus 5. So they're real numbers. Imaginary numbers, by the way, should use different color for imaginary. If I said the square root of negative 25, well, we can't get that, right? There's no numbers in the real number system that can give us negative 25, the square root of negative 25, so we say it's not real. Not real meaning it's not real because it's not a real number, not that it's not real, which is a little confusing, but it'll make sense once we get to imaginary numbers. Again, they're not fake imaginary numbers. And they've been around since the 1500s. They've been around a long time, since the 1500s. A man named Cardano in the 1500s, an Italian astronomer or mathematician, and also Bombelli, if you're curious about these two. Anyway, let's move on. So we'll stick with the real numbers for this video until we get to imaginary later on in the course. Let's clear this out again. Clear it all. You can always go back. We'll keep switching the color. So part of the real numbers, oh, this one's vibrant. There we go. A little neonness to it. We can have rational numbers. They can either be rational, or what do you think the other one would be? Irrational. Remember, irrational numbers are real numbers. They're not imaginary numbers. Don't get those two confused. We're just talking real numbers now. So real numbers can be expressed. They can be expressed as a quotient, like division of two numbers, of two integers. Remember? Two integers, any number that's not a decimal or a fraction. Like, for example, 1 over 2. It's a fraction. Well, that's rational. 5 is rational. You know why? Because 5 is 5 over 1. It's a rational number. When we talk about irrational, we'll change the color for irrational, they can't be expressed as a quotient. Can't be expressed as a quotient of two integers. Well, let's make it more simple. Or simpler, we should say. Before I told you, square root of negative 25 is not irrational, it's imaginary. So don't get these two confused. Not that. But the most famous irrational number is pi. You probably learned pi going way back to 6th grade when you tried to find the area of a circle. Right? So pi, some people just use 3.14 to estimate it, but it doesn't end, right? It's 3.14, 15, 92, 65, so on. ... goes on forever. Does not end. Does not terminate. Does not end. Does not repeat with a pattern. There's no pattern to it. So if it does not terminate and it does not repeat with a pattern, it's irrational. Like pi and phi. Talk about phi, right? Phi looks like this. Sometimes it's just written like that. You might get that confused. Well, isn't that an empty set? Well, that's the letter phi. Also, phi is the golden ratio. 1.61833 ... doesn't end. And the golden ratio is a way in which there are certain proportions in nature, which we'll talk about later on in other videos. Let's talk about the real numbers a little more rational, and we'll go back to irrational. So we said 1/2, 5, 5 over 1. Let's get back our pen over there. 5.2 is rational because it terminates. It's just 5.2. It ends. What do you think about this? 3.2 with a line over it. What is that? Is that rational? Does it terminate? No, it doesn't terminate. But it repeats with a pattern. The pattern is 2. It's just 2, 2, 2, 2. That's the pattern. The pattern continues. So it is rational. Let's do a few more. Let's clear this out. Stick with the reals. Again, the real numbers and rational. So 3 is rational. 3.25 is rational. That terminates. 3.256 with a line over that, that's rational because 256 repeats. It's 3.256, 256, 256, 256 forever and a day. Even if you had something 3.21985 and then all of a sudden it repeated 2198, well, I said 5 when it's a 7. I meant to say 5. So we could just say this is just 3.21987 with a line over the whole thing. So it's repeating. 3.21987 will repeat. The 21987 will repeat, so it is rational. What do you think if I gave you, let's give you a hard one. What should it be? This one's a good one. What if I gave you 0.010010001000001 ... Is that rational or irrational? What do you think? Well, it's actually irrational. Why? Because there is a pattern. You think, well, there's patterns here. You can see a pattern happening. You do see a pattern, but the pattern doesn't repeat. Does not, lost the S, does not repeat. And we mean the pattern does not repeat. So this is irrational. This type of question appears on SATs sometimes. So look out for that one. All right, so in simple terms with rational numbers, if they terminate like 3.2 or 3, or if they repeat with a pattern like 3.25, 25, 25, 25, and so on, then it's rational. If they do not repeat with a pattern, if they do not terminate, or they do not have a pattern that repeats, then it's irrational. And let's look at some more irrational numbers. So let's erase that. Go back to the irrationals. We couldn't erase it. There we go. And so, what if I said the square root of 2? What do you think that is? Well, in these square roots, right, the square root of 2 is irrational, right? But the square root of, let's say, 36, we know that that's a perfect square because you can find two numbers, two of the same number, multiplied together to get 36, right? This is plus minus 6. 6 times 6 is 36. And negative 6 times negative 6 is 36. But the square root of 2, you won't find that. So the square root of 2 is irrational. Irrational. Of course, the square root of 11 and square root of 3, they're all irrational. So you should know what irrational and rational are. What if I gave you, let's say I gave you 5.218 and the line is over the 18 only. Do you think that's rational or irrational? What do you think? Well, this is rational because, yes, even though the 18 is repeating forever. There's a pattern that's repeating, so this is rational. Now, so we have our real numbers, and then we have our rational numbers. We also have irrational numbers. And under the rational numbers, we can go down with integers, which we talked about before. We can have integers, we can have decimals. break this up here. Or we can have fractions, right? And again, integers or any number that are not fractions are decimals. And then we can have whole numbers. Because remember, integers could be negative. -5 is an integer. But whole numbers are only positive. They're all positive numbers. They're all positive integers, I should say. They're all positive integers and 0. Because 0, well, 0 is an integer, but 0 is not positive. It's not negative either. So all the positive integers and 0 are the whole numbers. And then, of course, we have our natural numbers, which are just 1 to infinity. 1 to infinity and beyond. And, of course, there are integers also. All right. The last topic we'll talk about is notation, which is we mentioned before. So let's clear this out. Get to notation. Let's clear it. Change the color. So the first notation is roster notation. And you've seen it before in the video. Roster notation has those braces. And so let's say, for example, we had 2, 4, 6, 8. And maybe this was all even digits. Right? That's all the even digits. 2, 4, 6, 8. In roster notation, just with the braces and so forth. And it's finite. We know it's finite because that's all there is. Now, infinite is hard to put into roster notation. So that's why you can use another notation called interval notation. Interval notation. So let's say we had, we wrote out this thing saying all integers greater than 3, but less than or equal to 30. Or any number, doesn't matter. So in interval notation, you're going to see a parentheses and you can see a bracket. So if you see parentheses, it means that the number is not included. Because it says greater than 3. That means we don't include 3. So we're going to have a little parentheses before the 3. A little comma there. And then the 30, we're saying is included because it says less than or equal to. So the 30 will have a brace. Sorry, a bracket, not a brace. That's a brace. So we just wrote that in interval notation. Let's do it again. Let's do a couple of them. Erase this. What if I say all integers greater than or equal to 7, but less than 100. How would you write that? That's our set. All integers greater or equal to 7, but less than 100. In interval notation. Now, we are going to include the 7, so we'll have to put a bracket because it says or equal to 7, but it says less than 100, so we don't include the 100, so we'll put a parentheses, and that's in interval notation. Okay, the next notation is set builder. Set builder. In fact, let's clear this out and I'll do it again. Change the color again on us. There we go. So, set builder notation, the third one, set builder notation. So let's say we said it'll have something like this. It'll say it'll have a brace And then it'll have a x, and that x is an element of the set. And then it will have this line coming down. That means such that. We'll talk all about this. Such that. And x will be, well, let me just write something out. We'll say this. So if you see something like this, here we're saying that x is an element of a set. So x could be what it says. X is going to be greater or equal to 8. So x could be 8, could be 9, could be anything all the way up to 300. That's a 300. Doesn't look like a 3, right? Let's make it an 8. Why not? There we go. Get that out of the way. Now we still need to clear this up. So in set builder, we're saying that the elements of the set, whatever they are, x, any element in the set x, what about that, such that, not such then, such that, x is greater or equal to 8, but less than or equal to 800. But we still need to clear this up, and we'll say x is a element, or is an element. That's what that symbol means here. It looks like a Greek letter, but it means that's an element, and then we'll have a letter denoting natural numbers. Or it could be anything. It could be z. Remember, z meant integer. If I said we have x is an element of the set where x is greater than 2, but less than or equal to 5, you could put that in interval notation. You can put it in set builder notation. But in set builder, you just need a little more information, and you can say x is an element of z. What's z? Remember what z means? Integers. How would you write that? See what you can do with that. Pause the tape, and what I'll do is I'll clear this part out here. Well, that's not working. I need to have a better eraser. What's going on here? All right, I have terrible eraser skills. Should make a video on eraser skills. Well, we could just spend a couple of minutes just looking at me erase things. Anyway, let's not do that. So again, x is an element of the set where x is greater than 2. So we know x is greater than 2. Let's get a different pen going here. What should we use? We'll use that. So how did you write it? So remember, x such that, well, what about x? What about x, right? And let's look at the numbers. It's greater than 2. So we have the 2 here, and it's greater than 2. X is greater than 2. It says it's greater than 2. It doesn't say anything else about it. But it's less than or equal to 5. And then we had a criteria. X is an element of integers, z. By the way, it should be, that's how it should look like, that element sign. So that's set builder notation. Okay, that's our first video today.